Good evening, sir.
Good evening, ma'am.
Good evening, sir.
Yeah, Jay, good evening. Let's start, Ajay.
Yes, sir.
Last class, we were learning about
Sir, time and reaction, sir. You finished it, sir.
Yeah, I finished it. This Riemann reactions, and I told you there are two Riemann reactions. One is phenol, chloroform, and sodium hydroxide, which gives salicyl aldehyde. The other one is phenol, carbon tetrachloride, and sodium hydroxide. It gives salicylic acid. We learned the mechanism last class in detail. We have learned it, so no point in again talking about it. So the next reaction is Lieberman's. Sorry. Next reaction is Lieberman's reaction. Can you see the screen?
Yes, sir.
Yes, sir.
The Lieberman's reaction. It was there for practicals, but we don't do it in the practicals now, right? When phenol is treated with sodium dissolved in concentrated sulfuric acid, a red coloration appears, which changes to blue on adding aqueous NaOH. This test is called as a Lieberman's test. It is for the detection of phenols. Now, sodium, when phenol is treated with sodium dissolved in sulfuric acid, sodium dissolved is since not a direct metal, sodium nitrite, NaNO2, in sulfuric acid gives sodium sulfate, giving you nitrous acid. This nitrous acid reacts with phenol. Phenol, we can represent it like this. This is OH, phenol, we have represented like this. And we'll show one of the hydrogen atom here at para position. Nitrous acid, I can write it as OH and N double bond O. HNO2 is called as nitrous acid. So what happens is this phenol reacts with the H and OH gets eliminated as water, and then in place of H, N double bond O goes. So you get a phenol benzene ring like this. You get OH and you get N double bond O. This undergoes rearrangement. When we say this undergoes rearrangement, the hydrogen atom of this OH group, phenol is acidic in nature, therefore this phenol gives you what? H plus ions. This H plus ion will attack oxygen. This double bond shifts back on nitrogen. And also, since hydrogen goes, there will be a double bond formed between oxygen. So you get oxygen, double bond, a benzene ring. You have nitrogen and carbon double bond, single bond OH. So this is an intermediate compound. So what happens is this OH of the phenolic group attacks the oxygen. When it attacks the oxygen, OH is formed. Oxygen can have only two bonds. So therefore the pi bond breaks and moves towards what? Carbon and nitrogen. Therefore this is an intermediate compound. This intermediate compound further reacts with phenol. So phenol, we can write it as OH, and this is also, I can represent an H here. What happens? Now this H and this OH gets eliminated as water. When this H and OH gets eliminated as water, what's the product we get? The product what we get is O double bond benzene ring, sorry. O double bond benzene ring, double bond N. This OH and H is eliminated. So you get a single bond, a benzene ring, and you get OH. You get OH. This, when it's allowed to react with sodium hydroxide, this is called as indophenol. This indophenol is red in color. When this is alkalinized or added NaOH, what happens? Water gets eliminated. When water gets eliminated, there is this OH, and this H gets eliminated. In place of H, sodium goes. So you get a double bond O, a benzene ring like this, double bond N, single bond, a benzene ring like this, and ONA. This is blue in color. So these reactions are not in syllabus and you don't have to worry about it. But remember, Lieberman's test is a test for phenol. So when phenol is treated with sodium dissolved in sulfuric acid, simply understand phenol in acidic medium, it is red in color. Then when you alkaline that by adding sodium hydroxide, the color changes to blue. Red color is because of indophenol and blue color is because of this complex molecule form. That is what you should remember based on a test called as Lieberman's test. Now these reactions are important. The next reactions are simple and very important. The first one is reaction of phenol with zinc dust. Reaction of phenol with zinc dust. This is phenol, C6H5OH. This is an important question for 12th standard. When this is heated with zinc dust, they can ask you this question for 2 marks or they can ask you for 1 mark. They can ask you what happens when phenol is allowed to react with the zinc dust, or explain the reaction between phenol and zinc dust. Or they can ask you for 1 mark, what is the product formed when phenol is treated with zinc? So when phenol is heated with the zinc dust, fine powder of zinc, the zinc and oxygen gets eliminated as zinc oxide. So when they get eliminated as zinc oxide, what is left out? This hydrogen is along with the carbon. Therefore, the product formed is benzene. So they can ask you a question, name the product formed when phenol is treated with zinc. It is benzene. Or they can ask you for 2 marks. This reaction is important. The next reaction is oxidation reaction. Oxidation of phenol with chromic acid. Chromic acid is a strong acid than sulfuric acid. It is a mixture of potassium dichromate and concentrated sulfuric acid. Chromic acid is a mixture of potassium dichromate and concentrated sulfuric acid, or it's a mixture of sodium dichromate, Na2CrO7 plus concentrated sulfuric acid. Sodium and potassium belongs to the same group, therefore the properties are same. So chromic acid is a mixture of potassium dichromate and sulfuric acid. So phenol, when you oxidize with chromic acid, it produces a conjugate diketone known as benzoquinone. What is conjugate system? A system having alternate double and single bond is called as conjugated system. So in the resonance structures, we would have learned a term called as conjugated system. Now this is benzene. This is phenol, sorry. When this phenol is oxidized using chromic acid. So what we get is you get a benzene ring like this, a double bond here. The positions of double bond changes. You get O and you get O. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond. So alternate single bond, double bond. This kind of molecule is called as conjugated diketone. Since we have 2 ketone groups, it is called as diketone. C double bond O, C double bond O, ketone group. And the name of this molecule is benzoquinone. The name of this molecule is benzoquinone. So phenol and oxidation with a strong oxidizing agent like chromic acid, all right, benzoquinones are formed. Followed?
Yes, sir.
Yeah, we
Yes,
will
sir.
have some more questions, some more topics, and have space here. After that, we will learn some of the questions. So I'll erase this part. So some more properties we will learn, and then we will see the question part of it. Now, why phenols? Maybe the question can be like this. Explain the acidity of phenols, alcohols and phenols. We will learn the heading as acidity of alcohols and phenols. Why are we talking about the acidity of alcohols and phenols? Because both contain what as a functional group? OH as a functional group. So the acidic character of water, alcohol, phenols is due to the polar nature of OH bond. Water is also acidic in nature. Why water is acidic in nature? Because of the polar OH bond. You should know that water behaves like an amphoteric substance. Ampholites, it can behave like acid, base, or base. All right, generally water is neutral nature, but water can behave like an acid or a base. Why water is behaving like an acid? Because of the polar nature. What is polarity? The charge difference between the two atoms is called as polarity. Oxygen is highly electronegative. Therefore, the bonded pair of electrons will be pulled towards oxygen, and hydrogen gains positive charge. This is polar. Likewise, when we talk about the alcohol also, the molecule is polar. So alcohol is represented like this, ROH. Now R is electronegative than hydrogen, therefore oxygen gains negative charge. Due to the polarity in case of alcohol, the molecule alcohol exhibit acidic character. Likewise, in case of phenols, we can represent phenol like this. This is O and H. In phenol also, you can see oxygen is electronegative and hydrogen is electropositive. Therefore, all these three shows acidic character. All these can give H plus ions. Since H plus ions can be given, therefore, it will be called as what? An acid. According to Bronsted-Lowry theory, proton donors are called as a base. Now, I can say that all these gives protons to a strong base. When these are allowed to react with a strong base, it all gives proton. Therefore, all these show acidic character. Proton donor is called as an acid according to Bronsted-Lowry theory. Proton acceptor is called as a base. Now, alcohols and phenols show acidic character for the reason the polarity between the OH bonds, first point, and all of these, when it's allowed to react with a strong base, it gives proton. Therefore, they are all acidic in nature. Now, explanation for the acidity. Explanation for acidity of alcohol. Explanation. Now, you should remember, there are 2-3 points which we are going to learn later. Now, alcohol, if alcohol is dissolved in water, ROH is the representation of alcohol. If this alcohol is dissolved in water, it dissociates to form RO minus and gives you H3O plus. It gives you RO minus and H3O plus, where R is an alkyl group. Where R is an alkyl group. Now, when I say R is an alkyl group, all alkyl groups are electron releasing group or electron donating group. It will donate electrons. So when they are electron donating group, it will experience plus I effect. That is positive inductive effect. And it makes the OH bond stronger. OH bond stronger. Then the OH bond in water. Then the OH bond in water. The abstraction proton becomes difficult, hence alcohols are weaker acid than water. That is the abstraction. I'll tell you what is this. The abstraction of proton, that is H plus ion, protons, becomes difficult. Hence, alcohols are weaker acid. Weaker acid than water. Alcohols are weaker acid than water. We've been learning that water is amphoteric. But here with this explanation, we understand that alcohols are much weaker than water, acidic character. Why? Now, because an alcohol is represented as ROH, we learned that R is an alkyl group. When R is an alkyl group, we also learned that R is an electron releasing group. When R is an alkyl group, if electrons are released towards hydrogen, the OH bond becomes stronger. When the OH bonds become stronger, an acid is a chemical substance which donates proton. An acid is a chemical substance which releases proton. But here what happens? Since alcohol is an electron donating group, the bond strength between oxygen and hydrogen increases. When the bond strength between oxygen and hydrogen increases, the molecule to release H plus ion becomes more difficult. Since this molecule to release this H plus ion becomes more difficult, the acidic character decreases. The acidic character decreases. You should also remember the order of the acidic strength for an alcohol. The order of acidic strength is tertiary alkoxide ions or tertiary alcohols are stronger than secondary or stronger than primary, and primary is stronger than methyl group, methoxy group. So this is the strength of an alcohol, acidic strength of alcohol. Now we have to compare the acidic strength of alcohol with phenol. Is that followed so far? Alcohols, water,
Yes, sir. Follow, sir.
phenol,
Yes, sir.
all the three are acidic in nature, but alcohol is much weaker than acid, much weaker than water, because in case of alcohol, R groups are electron donating group. Since R groups are electron donating group, the OH bond becomes stronger. Therefore, the molecule will not release H plus ions easily. But in case of phenols, we will learn the explanation for acidity of phenols. Explanation for acidity of phenols. Now, in case of phenols, we represent phenol molecule like this. No, I'll draw a little bigger. Now, I'll erase this part and write, because we require a long explanation. Resonance structures I have to teach you for phenols. Sometimes they can ask you the resonance structures for phenols also. So I want some bigger place. So I'll erase this and explain. Now, phenol, we represent phenol like this, a benzene ring, double bond here, double bond here, double bond here. O, oxygen has two lone pairs of electrons, remember, and a hydrogen. This is phenol. This is the representation of phenol. Now, and this phenol is fairly stronger acid than alcohols. But phenols are much weaker than carboxylic acid. Phenols are stronger than alcohols, acidic character-wise, but they are weaker than carboxylic acid. The main factor for acidity of phenol is its resonance. The main factor for acidity of phenol is resonance. Now, what is this main factor for acidity of phenol is resonance. Now, I'll write it here. Excuse me. Now, phenol, as I have written the structure, we will write, now the phenol is C6H5OH. This is phenol. This phenol will undergo partial dissociation to form phenoxide ion, O minus. Already you have a lone pair of electron, O minus, and you get H plus ion. This is called as phenoxide ion. This phenoxide ion which is formed is resonance stabilized. When we say resonance stabilized, this undergoes resonance stabilization. Therefore, this molecule gives you what? H plus ion. So when the molecule gives H plus ion, anything which donates a proton will be called as an acid. So we get phenol when dissolved in water. This phenol will dissociate partially to form phenoxide ion, or not phenoxide, it's called as phenate ion. It's called as phenate ion. Phenoxide is O, and a phenate ion. This phenate ion is resonance stabilized, meaning H plus ion will be released as such. Now, if you take an alcohol, C2H5OH, this alcohol also undergoes dissociation to form ethoxide ion, C2H5O minus and H plus. This ethoxide ion is not stable. It is not stable because it's not undergoing resonance. Therefore, what happens? Immediately there will be a reaction between H plus and OH minus to give you alcohol. Therefore, alcohols are very weak acid compared to water. That is what we learned. But in case of phenol, phenol is a stronger acid than alcohol, but weaker acid than carboxylic acid. Now, this is the representation of phenol. Now, phenoxide ion we can represent like this. Phenoxide ion. What's that phenoxide ion? Now we have, this is phenol. Phenol dissociates to form a phenoxide ion. I've represented a phenate ion here. Now, in order to write the resonance structures of a phenate ion, this H plus is gone. That means this minus sign indicates 2 electrons. So we'll represent 2 electrons like this is phenate ion. This is phenate ion. This is the first resonance structure of phenate ion. Now, what happens, you see, now this 2 electron or any 2 electrons comes and forms a bond between carbon and oxygen. When they form a bond between carbon and oxygen, what happens? A double bond will be formed. Now, a double bond will be formed like this. Like this. Like this, a double bond will be formed. And since both the electrons are moving here, only 2 lone pairs of electron will be there here. Now tell me, this is carbon 1. This is carbon 2, carbon 3, carbon 4, 5, and 6. Now carbon 1 has how many bonds? Carbon 1 has how many bonds? Carbon 1 has how many bonds?
So, 2.
2. Carbon 1 has how many bonds? Carbon 1. This carbon has 2 bonds with the carbon
Yes,
2, 2 bonds with oxygen, and 1 bond with the carbon 6. Totally carbon
yes, sir.
5
5,
bonds.
sir.
Can carbon have 5 bonds?
No, sir.
Carbon valency is tetravalent. So what happens is, when a pair of electrons comes towards carbon 1, the pi bond between carbon 1 and carbon 2 breaks. When pi bond between carbon 1 and carbon 2 breaks, this is carbon 1, this is carbon 2, 3, 4, 5, and 6. When pi bond breaks, what happens? Pi electrons are formed. These electrons, will it move towards carbon 1 or carbon 2? Think and answer me. This pi bond breaks because these 2 electrons are coming towards carbon 1. So pi bond breaks, pi electrons are formed. These electrons will move towards carbon 1 or carbon 2. Take a guess quickly. Huh? Anybody? Hello? Are you there?
Yes, sir.
Tell me these electrons will move towards which carbon, 1 or 2? It surely cannot go towards 1 because this electrons also coming towards 1. Repulsion will take.
Yes, sir.
This electrons will move towards carbon 2. When this electron move towards carbon 2, what happens? In simple word, I can tell the pi bond between 1 and 2 breaks, and what happens? These electrons which are moving towards carbon 2, so carbon 2 gains what charge? Negative charge. This is second resonance structure. So we'll go fast now. The third resonance, this minus sign indicates 2 electrons, remember. So this minus sign, 2 electrons move between carbon 2 and 3. When they move between carbon 2 and 3, the bond, double bond between carbon 3 and 4 breaks, and the electrons move towards carbon 4. So you get a benzene ring like this. You already have a double bond, oxygen here. The double, now this is 1, 2, 3, 4, 5, and 6. So a double bond is formed between 2 and 3. Therefore, carbon 4 gains what charge? Negative charge. Already 5 and 6, there is a double bond. This is the third resonance structure. Hoping so you followed.
Yes, sir.
The electrons, which is on the carbon 4, now goes or moves between carbon 4 and 5. When they move between carbon 4 and 5, the double bond between 5 and 6 breaks and pi electrons move towards carbon 6. So the fourth resonance structure will be a double bond here, double bond here, double bond here. This is negative. You have oxygen, and this is carbon 1 and this is carbon 6. Now, this is the fourth resonance structure. The fifth resonance structure. These electrons move between carbon 1 and 6. Therefore, what happens? The pi bond between carbon and oxygen breaks and pi electrons move on that. The fifth resonance structure will be a benzene ring, a double bond here, a double bond here, a double bond here, oxygen, single bond here. Oxygen has 6 electrons with a minus sign. 6 electrons with a minus sign. This is the fifth resonance structure. Look at the first and the sixth carbon atom. The first is not carbon atom, first and the fifth resonance structure. Now, in case of first resonance structure, double bond is between 1 and 2. Here, there's no double bond. The double bond is not there between 2 and 3, but here's a double bond. So it means compared to the first and the fifth resonance structure of phenate ion, the double bond position is what? Different. So this is called as resonance stabilization. Since this phenate ion undergoes this process, the H plus given by phenol remains stable. So acidity is because of the presence of H plus ions, right? We know that pH is negative logarithm to the base 10 of H plus ions. That is why phenols are stronger. Now, if you take alcohols are weaker than water. Water is weaker than phenol, and phenol
Sir, screen is not available.
not available.
Yes,
What
sir.
No,
We
sir,
can't
it's
see,
not.
sir.
Got scared, man. Suddenly you're telling so loudly. Got scared. All right, now
Sir,
is it-
now, yes.
Yes, sir. Now, yes, sir.
yeah, phenol, and phenol is weaker than carboxylic acid. Carboxylic acid. This is the strength, acidity strength. Alcohol is weaker than water. Water is weaker than carboxylic acid, and phenol is weaker than carboxylic acid. I hope that you understood the reasons why phenol is more acidic than alcohols. Correct? Now we have to learn the
Yes,
next
sir.
concept, and we will go for the questions quickly today. Few more, 2-3 points more I have to teach you with respect to phenols. We will learn that. Now you should remember, acidic is because of the ability of the molecule to release H plus ions. If a molecule can release H plus ions easily, it will be a stronger acid. If a molecule cannot release H plus ion easily, it is a weaker acid. So acidity is based on the strength or ability of the molecule to release H plus ions. Now, the heading is effect of substituents on the acidity of phenols. Effect of substituents on the acidity of phenols. So when we say effect of substituents are of two types. One is electron withdrawing group, the other one is electron donating group. Now you should remember, electron withdrawing group stabilizes the phenate ion and greater is the acidity. Now the first point is electron withdrawing group. Electron withdrawing group stabilizes the phenate ion. When I say stabilizes the phenate ion, the stabilization is because of resonance. Stabilizes the phenate ion, and increases, therefore, increases the acidity, or maybe we can write therefore increases the acidity of phenol. Acidity of phenol. Now, example for withdrawing group, electron withdrawing group. What are the example for electron withdrawing group? A strong electron withdrawing group is nitro group, cyanide, CHO, aldehyde group, ester group, or a halogen. These all are the examples for electron withdrawing group. So electron withdrawing group will increase the stability of the phenate ion, therefore increases the acidity. Now the magnitude of stabilization of phenate ion depends on the position where the substituent is present. If the substituent is present at ortho-para position, then the effect is more pronounced. So firstly, you should remember para-substituted products, para-substituted phenols are more acidic than ortho-substituted phenols, because electron withdrawing group, therefore it will increase the effect more pronounced at ortho and para position. So next is meta-substituted phenol, and then it will be phenol. So for an example, if I write para-nitrophenol, this para-nitrophenol will be more acidic than ortho-nitrophenol. See, all these are nitro-substituted products. Now, ortho-nitrophenol will be stronger than meta-acidic, more acidic than meta-nitrophenol, and meta-nitrophenol will be more acidic than phenol. Remember, electron withdrawing group stabilizes the phenate ion by resonance and increases the acidity. Likewise, if we talk about electron donating groups, the second one is electron donating groups. Electron donating groups. This electron donating groups destabilizes the benzene ring or phenol, destabilizes the phenate ion. Since it destabilizes the phenate ion, the acidity, it decreases the acidity of phenol. Decreases the acidity of phenol. Now, electron donating group, remember, all alkyl groups are electron donating group. Alkoxy group or electron donating group. So all these electron donating groups will decrease or destabilize the phenate ion and decreases the acidity. Now, for an example, what do you mean by destabilization? Just observe here. This is phenol. Sorry, this is a double bond I will show. This is double bond. This is phenol. This phenol, this OH group is an electron donating group. If I have a substituent here like CH3, an alkyl group, this also is electron donating. See, this electron will move here and this electron try to move. So what happens? Repulsion will take place. Therefore, what happens? The phenate ion becomes what? Destable. That is what it means. But here, in case of nitrophenols, just observe this. This is phenol. This is phenol. This OH is an electron donating group. Here, nitro group is also an electron withdrawing group. See, it is donating and this is accepting. Here, both are donating. Therefore, the phenate ion becomes destabilized. Hence, the decrease in what? Acidity. In case of electron donating group, which destabilizes the phenate ion and decrease the stability, so the order is like this. Phenol is more stronger than metacresol. So metacresol is nothing but phenol. At meta position, we have CH3. Phenol is stronger than metacresol. Metacresol is more acidic than paracresol, and paracresol is more acidic than orthocresol. This is the acidity of substituted phenols, electron donating group and electron withdrawing group effects. Followed, some more reactions we have. We will learn the reactions maybe after some questions, or I'll teach you the reactions also now itself. Reactions are there here. This is for ethers. All right, we'll have to learn some more reactions. Only then we can go for these questions. So I hope this acidity concept you followed.
Yes,
Students.
sir. Followed, sir.
Yeah. Others, madam. Nobody is there in the class. Huh? Oh, 1 minute. Just you give me 1 minute. I'll erase this and then we'll start. Some of the reactions of phenols. The first reaction here, again, what we're going to learn is called as acetylation. Acetylation. What is this acetylation? Reacting phenol with acid chlorides is called as acetylation. Now we can represent a phenol like this. This is the representation of a phenol. When this phenol is allowed to react with acetyl chloride, this acetyl chloride has a formula CH3COCl. CH3COCl. We will write like this: ClOCCH3. CH3COCl for understanding simple way. So what happened? This H and this Cl gets eliminated as HCl. In place of this H, carbon gets bonded. When carbon gets bonded, what we have? You have a phenol, a benzene ring, you have oxygen, you have carbon, you have this oxygen and through a double bond, and you have CH3. This is called as phenyl acetate. Phenyl acetate. The IUPAC name for this molecule is phenyl ethanoate. Phenyl ethanoate. So when phenol is treated with acetyl chloride in the presence of a pyridine catalyst, the catalyst what they use is pyridine. When phenol is heated with acetyl chloride in the presence of pyridine, phenyl acetate is formed. This reaction is called as acetylation. So reaction of phenol with acetyl chloride will be called as acetylation. Similarly, when this phenol is reacted with benzoyl chloride is also an example for acid chloride. So from benzoic acid, if the OH group is replaced by Cl, then it's called as benzoyl chloride. See, benzoic acid is C6H5COOH. If this OH is replaced by Cl, then the molecule what we get is called as benzoyl chloride. Now what happens, the same reaction, this will be called as benzylation. Benzylation. Now when phenol is heated with benzoyl chloride, CH3, CH3CO, C6H5. There's a benzene ring here, C6H5. In the presence of pyridine, in the presence of NaOH, here it is not pyridine, in the presence of sodium hydroxide. What happens? This H and this Cl gets eliminated as HCl. In place of H, carbon goes. So you get a benzene ring, you get oxygen, you get C double bond O, C6H5 plus H2, HCl, sorry, plus HCl. This is called as phenyl benzoate. This reaction, benzylation, is also having a specific name. That name is called as Schotten-Baumann reaction. Schotten, Schotten-Baumann, Baumann, Baumann reaction. So benzylation is also called as Schotten-Baumann reaction. All right. So few more reactions we will learn, and then we'll start with the questions. Followed with this, Ajay.
Yes, sir.
Dhanlakshmi is there. Others are there.
Yes, sir.
Are you
Yes, sir.
following?
Yes, sir.
Yeah. Few more reactions, and then we'll solve some of the questions possible. Now, the next reaction is reaction with PCl5. Reaction with phosphorus pentachloride. PCl5 is phosphorus pentachloride. When phenol is treated with phosphorus pentachloride, it gives triphenyl phosphate as a major product and a small amount of chlorobenzene. So phenol with PCl5, phosphorus pentachloride, it gives triphenyl phosphate as the major product. As the major product, and a small amount of chlorobenzene as a byproduct, minor product otherwise. It is less than 1%. Chlorobenzene formed will be less than 1%. So phenol, we know that it is C6H5OH, phenol. When this phenol is treated with PCl5 or heated with PCl5, we get chlorobenzene. This chlorobenzene is less than 1%. Chlorobenzene formed is less than 1%. It is a minor product. Triphenyl phosphate. So the formula for triphenyl phosphate is PHO thrice P double bond O. Triphenyl phosphate. What is this pH? This pH stands for C6H5, benzene 3. pH C6H5O thrice P double bond O. This is called as triphenyl phosphate. This triphenyl phosphate is a major product. So this is the reaction of benzene with phenol with phosphorus pentachloride. The next reaction we will learn, and then we'll continue with some of the questions possibly. Now, the next question is when phenol is acidic in nature. We've been learning when phenol is heated with or allowed to react with ammonia. Ammonia, I will write it as HNH2. This is NH3 ammonia. In the presence of anhydrous zinc chloride, when you heat it, anhydrous zinc chloride is a dehydrating agent. OH and H gets eliminated as water. So in place of OH, NH2 goes. Therefore, you get a benzene ring and you get NH2. This is called as aniline. So these are the reactions of phenol. I think we have learned the reactions of phenol, bromination, nitration, all that we have learned. The products also we have learned. Now we will learn some of the questions based on phenol, and then we will see what can be done. The first question is, where's the question? Yeah. The increasing order of acidic strength, paramethoxyphenol 1, paramethylphenol 2, and paranitrophenol. The strength the increasing order of their acidic strength. What is the increasing order of the acidic strength? Methoxy. See, I was discussing that electron donating group will decrease the strength of phenol. So this is methoxy. Maybe I'll write it like this. 1 minute. This is phenol. Paramethoxy. Methoxy is OCH3. It's a strong electron donating group. Now this is paramethyl phenol. Paramethyl phenol. At methyl position you have CH3. Next what we have is paranitrophenol. Now you should remember this methyl group and alkyl groups are electron donating group. Nitro group is an electron withdrawing group. NO2 is an electron withdrawing group. I told you electron donating group decreases the strength, acidity of phenol. Electron withdrawing group increases the acidity of phenol. Now in this three, this will be the strongest, no doubt about it, because NO2 is an electron withdrawing group. It stabilizes the phenate ion. But here, both are what? Electron donating group. Methoxy is electron donating. Methyl group is also an electron donating group. Therefore, they should decrease the strength. But which is a stronger electron donating group? Alkoxy groups are stronger electron donating group compared to alkyl groups. Therefore, this will be much weaker than methyl phenol, and paramethyl phenol will be much weaker than paranitrophenol. Hence, the answer for this question will be option D. Order. First one will be weaker, increasing order thereafter. This is weaker, next it is, and strongest is nitro group. Therefore, the answer for the question is option 4. Arrange the following compounds in order of decreasing acidity. Arrange the following in the order of decreasing acidity. That means strongest to the weakest acidity. So we know that, see, this is electron donating group, this is electron donating group. Stronger electron donating group is nitro. So this will be the strongest. So it will be option, this one, third one, this will be the strongest. Then compared to first, because chlorine is also an electron withdrawing group. Nitro is also an electron withdrawing. But just now we learned about methyl and methoxy. So methyl will be stronger than. So the order for this is option C. You followed this, what I'm telling students?
Yes, sir.
Yeah. The next question. When phenol is treated with excess bromine water, you tell me what's the product you get. I have taught you in this class. Not in this class, the previous class we have learned in detail. Tell me.
Sir.
Tell me.
Sir, ortho and para bromophenol, sir. Option B. So option B.
Option D, correct. Option D. Now, if you use bromine and carbon disulfide, you get two products, ortho and para-bromophenol. But when we use bromine water, so I told you this is OH, phenol, this is H, this is H, and this is H. Now, when this is allowed to take bromine water, aqueous bromine, so what happens? I can write one bromine here, 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 one bromine here. HBr, HBr, HBr gets eliminated. 3 HBr in place of H, bromine, bromine. Here also the bromine. So you get a white precipitate of 2,4,6-tribromophenol. You will get this product. So bromine is red color. Red color will disappear. All right.
Yes, sir.
Yes, sir.
The next question. Phenol reacts with bromine. Just now we learned. Phenol reacts with bromine in carbon disulfide. or carbon tetrachloride or solvent. So at low temperature, it'll give you what? A mixture of ortho and see, with bromine water, you get only one product, a white precipitate of 2,4,6 tribromophenol. But when bromine is adulterated with carbon disulfide as a solvent, when phenol is treated with bromine, the presence of carbon disulfide as a solvent, you get a mixture of ortho and para bromophenol. All right. Can we go for the next question? This is same. Phenol is treated with a solution of mixture of KBr and KBrO3. Bromate, potassium bromide and potassium bromate. The major product obtained in this reaction is, now it is confusing, but the question is, answer is simple. KBr reacts with KBrO3, potassium bromide, to form bromine aqueous, Br2 aqueous, Br2 aqueous. When we have bromine in aqueous medium, what's the product you will get? What's the product you will get? We learned it now. When aqueous bromine we are using, what's that you get? 2,4,6 tribromo.
So 2,4,6
Yeah, therefore the answer will be what? Option D,
So option D.
2,4,6 tribromophenol. The next question, phenol on reduction with hydrogen in the presence of nickel catalyst. This is phenol. This is phenol. When this is hydrogenated in the presence of nickel catalyst. Now this hydrogen I show like this. One hydrogen attacks this carbon, and the other hydrogen attacks this carbon. Pi bond will break. Second molecule, if I represent, one hydrogen attacks this carbon, the other hydrogen attacks this carbon, the pi bond breaks. The third hydrogen molecule, if I write, one hydrogen attacks this carbon, the second hydrogen attacks this carbon, pi bond breaks. So what's that you get? You get hexagon and OH, because pi bonds are broken and hydrogen are added. So what's that you have here? You have CH2, here you have H, here CH2, here it is CH2, here also it is CH2, and here also it is CH2. So the name of this molecule is cyclohexanol. It's a cyclohexane. So this is cyclohexane, a ring compound, cyclohexane. And if I have OH group here, it will be called as cyclohexanol. Called as cyclohexanol. Hence the answer for this question is option D. All right. The next question. Which of the following is formed when phenol is exposed to air? When phenol is exposed to air, it undergoes oxidation. When it undergoes oxidation, you get a diketone. What's the diketone called as? The diketone will be called as benzoquinone. Diketone is called as benzoquinone, parabenzoquinone. Hence the answer for this question is option B. All right. We'll learn the next set. Okay. We'll one more question, we'll finish. Phenol is less acidic than acetic acid, paramethoxyphenol, paranitrophenol, ethanol. Phenol is less acidic than option A and B. Acetic acid. Acid is stronger than phenol. Nitrophenol is stronger than phenol. So the answer will be here, A and B. Some of the competitive exams like IIT or JEE, they have multiple right answers. So here, A and C are right. Paranitrophenol is stronger. Acetic acid is also stronger than phenol. We will learn the next set of questions in the next class, maybe possibly tomorrow. We will stop the class here. All right.
Yes, sir.
Bye, everybody. Bye.